Okay, so recording is on. So we talked in the last class about a definite integral. And the definite integral is, well, I mean, I can write something real quick here. You know, you have an x-axis and a y-axis. Okay. And you have some function. Maybe the function does this. Okay. And you're interested in, well, if you write down the integral from a to b, the definite integral from a to b of f of x dx. Okay, draw it a little, let me do that a little bit better. Okay, what does this definite integral mean? What does it mean? Well, in terms of our picture up here, if we were to add the first area and the second area, which is the area bounded between the function and the x-axis, the sum of those areas would equal the definite integral here. That's what that means. And of course, you're going to have here a positive area, because that area is above the x-axis, and a negative area. And the sum of those two areas is equal to the value that the definite integral here gives you. Now, what we did, of course, in the last class was we said, let's evaluate this definite integral. And what we did is we actually wrote the integral as the limit of a Riemann sum, right? This is in your notes. It's in the recording from last week. We write the integral as a Riemann sum, the limit as n goes to infinity of this Riemann sum. The sum where I goes from 1 to n of f of xi times delta x. So you're adding up the sum of a bunch of areas of rectangles. You're adding up the areas of rectangles, and as n goes to infinity, the width of each rectangle, delta x, gets smaller and smaller. And so in the limit, since delta x gets smaller and smaller, the rectangles get thinner and thinner, and they fit better under the curve. And so as the limit as n goes to infinity, this sum is going to equal the true definite integral. Okay, and we worked it out. But to work it out, it required us to compute the limit of this Riemann sum. And to actually compute the Riemann sum, we had to use expressions. We had to, we went through the steps here, and we had in the end to use expressions that are in the book in section 5.2 for the sum of I equals 1 to n of I cubed and the sum of I equals 1 to n of I. Okay, and those formulas are given in the beginning of section 5.2, and this was the one formula here, and this was the other formula here. And based on that, then, we were able to get a function of n on the right side here, and we took the limit of that, and we could evaluate it, and we were able to get our value for the definite integral. Okay, how many recall, I mean, I reviewed it, but how many definitely recall doing that last class? And in your homework, you had a few problems too with that. Okay, so how many definitely recall doing that? Okay, Betsua recalls it, and Joe and Rodrigo and John. Okay, all right, Ian. Thank you. So this is nice. This is nice that we can take the limit of a Riemann sum. Thank you, Sebastian. We can take the limit of a Riemann sum and get out an answer for the definite integral. But it is time consuming, and Joe will have to. You look back in the, why is Joe saying in the limit 1 over 1 plus n as n goes to infinity is just 1. And that's how you get 1 squared. Joe was asking about how we got the 1 squared there. So, very good, very good. And so, you know, we can compute definite integrals by taking limits of Riemann sums and then, you know, going through all the steps, you know, just like, you know, we did here, you know, on that page, you know, on this page here, and then on the next page. I mean, we can do this. But the problem is it's rather time consuming. It is rather time consuming. So we would like to have a quicker way to compute a definite integral. And section 5.3 in your textbook talks about a theorem called the evaluation theorem, which will give you a nice way to compute a definite integral. So let me go ahead into the ebook here. One moment. Just give me one moment here, class. One moment. Okay, I'm going to open up the ebook, and I'll have to share it with you, of course. Okay, I'm just finding it here. So we're going to section 5.3 in our ebook. So you can go there too as well. Okay. All right, and let me share that right now, the ebook. Okay, this is called the evaluation theorem. Section 5.3, the evaluation theorem. And what it says is that if you have a continuous function over some region, well, from A to B, okay, the function f is continuous on the interval from A to B, then the definite integral, computing the definite integral, simply just involves computing the antiderivative of the function at B and the antiderivative of the function at A, and then taking the difference. Okay, that's what this is. In other words, we can compute an antiderivative. Well, we can compute a definite integral by simply taking the difference of the antiderivatives of the function f of x at A and B. Capital F is, as you know, how many remember the notation for capital F being the antiderivative of a function f? How many maybe recall that in it was a while back, but Nicholas remembers it. You had antiderivatives back in I believe it was Joe remembers from the test. Well, yeah, there you go. Absolutely, section 4.8, right? Antiderivative. So this is really an amazing result because we don't have to find the limit of a Riemann sum anymore. We can just use the evaluation theorem. So I think it would be worth looking at the proof of this, just you know, to help you feel comfortable. But before I look at the proof, I do need to hold on here. I do need to talk about what's called the mean value theorem real quick. So the mean value theorem, let me just find it in the book here. One moment, class. Mean value theorem is in section 4.3. So what I want to do is bring up section 4.3 here. Okay, if let me just see here, 4.3. So I got to get to that chapter. Let me see here. Well, that doesn't look like what I want. One moment. Let me go into. So I was 4.3. Hold on here. Is we talked about derivatives and shapes of curves before. Okay, and I'm finding what they call the mean value theorem, because we're going to need it to prove this evaluation theorem in section 5.3. Let me just see if I can find it. It should be here. It should be here. Oh, it's way at the beginning. Okay, it's at the beginning. Here it is. Okay, now let me just see. Are you able to see this? Yes, okay. The mean value theorem. So what does the mean value theorem say? It says that if you have a function that's differentiable over the interval from a to b, meaning that it has a derivative, then there's a number c between a and b such that f prime of c equals the quotient of f of b minus f of a divided by b minus a. That's what it means. Okay, that's what that means. So pictorially, another way of saying it is f prime of c times b minus a is equal to f of b minus f of a. And the theorem, it's if you look at it graphically, it's a lot easier to understand. Okay, so I'm looking at figure 1 here. I'm looking at figure 1, where they have a function f from a that goes from a to b, and they have points a and b here. Okay, points a and b. So point A has the coordinate a, f of a. Point B has the coordinate b, f of b. And if you take the slope of that blue line segment that connects points A and B, the slope of that line segment would just be rise over run, right? Rise over run. So the rise would be f of b minus, and the slope's negative, incidentally, but the rise would be the f of b minus f of a over the run, which is b minus a. So that's what you had here. That's what you have right here. Hold on here. Yeah, you have on the right side, you have f of b minus f of a divided by b minus a. That's the slope of the line segment that connects points A and B. Well, what they do is between the values A and B, there's a point C between the values A and B, such that the derivative of the function when x equals c, that value of that derivative will equal f of b minus f of a over b minus a. Okay, and you can see that the tangent line to the curve when x equals c, that tangent line has the same slope as the line segment connecting points A and B. And that has to happen if you have a continuous differentiable function over some closed interval a, b. There's always going to be a point C between the values a and b, such that f prime of c equals f of b minus f of a over b minus a. So the mean value theorem is going to be important for proving the evaluation theorem. Are there any questions on that? Are there any questions on that before we go back to section 5.3? Okay, who's reasonably comfortable with that? Okay, thank you, Nicholas. Okay, Joe, good, good. All right, well then let's go ahead and go back then. Let's go back. All right, so let me see here. I got to go back into the ebook. Let's see. So let me just bring it up again. Okay, back to chapter 5. Okay, so now how do we prove the evaluation theorem? The proof is actually quite simple, quite simple. All right, but let me just show you an example of how it works. So, like if you wanted to find the definite integral from 0 to 1 of x squared dx, okay, you could find that using a Riemann sum. You could. But using the evaluation theorem, all you need to take is the difference of the antiderivatives of that function, x squared, at 1 and 0, and subtract. Well, the antiderivative of x squared is just, as you know, it's 1/3 x cubed. And so the evaluation theorem says the definite integral from 0 to 1 of x squared dx would just be equal to 1/3 times 1 cubed minus 1/3 times 0 cubed, and that equals 1/3. Okay, that's an example of how to use the evaluation theorem. How many like that? How many like that a little better than using Riemann sums? Okay, Trevor was real quick on his answer. Wow! Oh my goodness! Look at this. We got. Thank you, everybody. Wow! Wow! Everybody loves the evaluation theorem. Okay. Well, and you know, you're going to be using it a lot in calculus too, as well. So, how do we prove this lovely theorem? The proof is really quite simple. The proof's really quite simple. Okay, what they do is they take the difference of the antiderivatives of our function at b and a, and they express it as what's called a telescoping sum. Now this proof, I'm just going to sort of go through it rather quickly. I'm not expecting you to be able to prove the evaluation theorem, but I just want you to have just a little feel of why that evaluation theorem is true. You know, when you divide your interval from a to b up into subintervals, we let a equals x sub 0 and b equals x sub n. And so f of b minus capital F of b minus capital F of a is capital F of x n minus capital F of x naught. But what you can do is you can write this as a telescoping sum where you subtract f of x n minus 1 and add f of x n minus 1. You know, that equals 0. When you subtract and then add the same thing, it's 0. And you can subtract and add, like for instance, you can subtract f of x1 and add f of x1. You can do this for any number of points. And you can write capital F of B then minus capital F of A as the sum from I equals 1 to n of f of xi minus f of xi minus 1. Now here's what's important to note. F of xi, capital F of xi minus capital F of xi minus 1, sorry, capital F of xi minus capital F of x sub I minus 1 would, by the mean value theorem, equal the derivative of capital F at xi for some xi star that's between on the interval from x sub I minus 1 to x sub I, okay, times the difference of x sub I minus x sub I minus 1. Okay, so this is the mean value theorem says that the difference of these, of capital F of x sub I minus capital F of x sub I minus 1 is equal to the derivative of capital F of x sub I. Capital F is the antiderivative, right? So the derivative of the antiderivative evaluated at x sub I times the difference times the width of your interval. And that width of the interval is delta x. Well, the derivative f of your antiderivative, the derivative of capital F, is just lowercase f. And so this difference here of your antiderivatives at B and A can just be expressed as a Riemann sum. It can be expressed as a Riemann sum. And if we take the limit of the Riemann sum, we're going to get the integral, the definite integral. And therefore, the definite integral can be computed as by finding the antiderivatives. Sorry, let me say that again. The definite integral can be evaluated by finding the antiderivative of your function f, evaluating it at n points B and A, and taking the difference. And that's how the evaluation theorem, that's why the evaluation theorem is true. Okay. And incidentally, when you apply the evaluation theorem, you use this notation. Okay, and you'll see it in a few examples we're going to do. You'll see this notation a lot. Okay, so the book talks about some examples. Like one example they talk about is evaluating the definite integral of e to the x from 1 to 3. And we actually look in example 3 back in section 5.2, they actually wrote out a Riemann sum for this problem, but it was kind of cloudy how it wasn't clear how they evaluated the limit of the Riemann sums. They did evaluate it, but they said they used a computer algebra system. Well, you know, we don't need that. All we need to use is the evaluation theorem. That's all we need to use. So the antiderivative, or the definite integral from 1 to 3 of e to the x dx is just equal to e to the third. Well, it's e to the x evaluated at 3 and 1, and that's e to the third minus e. Okay, and that's what it is. Okay, are there any questions on that? All right, if they're not, then let's go ahead and look at a few examples here that I have. I want to read you this example because this is the example that I showed you earlier in the lecture where in the last class, we computed this, we evaluated this definite integral by taking the limit of a Riemann sum. And we found that the value was negative 6.75 for this definite integral. Well, let's see if the evaluation theorem will give us the same result. All right, so let me give you a moment to copy that down. Okay, and while we're doing that, let's see, Yaki, can you hear me okay?
Yes.
Good, good. Yaki, so just a quick thing, nothing bad, nothing bad. After class, do you have a moment? I had a question for you. But nothing, it's not, so yeah, it's not bad class, not bad. Okay. All right, very good. I'll chat with you just for a moment after class. Very good, very good. Okay. See, if I were in class, I would ask a student right in class, you know, so I'm just doing the same thing. And let's see, Betsua, can you hear me all right, Betsua? Let's see, Betsua, can you check your email, Betsua? I sent you an email, okay? Nothing bad, nothing bad. Okay, so let's go ahead and evaluate this definite integral here using the evaluation theorem. Okay, that's what we want to do. So I'll go to the next page. Okay, so what I'm going to do first, of course, is, I'm just going to find the antiderivatives of x cubed. The antiderivative of x cubed is just x to the fourth over 4. Okay. And then the antiderivative of 6x is just 6 times x squared over 2. And then I'm going to evaluate, so the entire, the antiderivative, what if I want the antiderivative of x cubed minus 6x, right? So to get that antiderivative, I can get the antiderivative of x cubed separately, the antiderivative of 6x separately, and then, you know, I got the difference here. So the antiderivative of x cubed minus 6x is just x to the fourth over 4 minus 6 times x squared over 2. And you had plenty of practice in finding antiderivatives on your exam and back in section 4.8. Okay. Okay, now we want to evaluate. So I'm going to call, just for the sake of notation here, this here, right, is the big F function, which is our antiderivative function. And of course, the x cubed minus 6x function, that's just little f of x. Okay. And so, you know, here we're using the evaluation theorem, you know, so this is, we're using, again, the evaluation theorem. And so this here, 3 to the 4th over 4 minus 6 times 3 squared over 2 is big F of 3. And then 0 to the 4th over 4 minus 6 times 0 squared over 2 is big F of 0. Okay, so I'm just trying to, you know, tie in here. The evaluation theorem for you. So what I'm writing here in the top right-hand corner is the general form of the evaluation theorem. Okay. And, you know, I've spelled it out for you here. Are there any questions here? All right. Well, so now we just evaluate the antiderivative at 3 and the antiderivative at 0. And this is just now math. This is just math. And Joe agrees. It's definitely easier than than using the limit of the Riemann sums. Absolutely it is. And this is why mathematicians came up with the evaluation theorem. Because they wanted to, you know, it's always good if you can make your life a little easier. Good question. John asked, can you, yes, so the final exam, of course, chapter 5 is going to be on the final exam, and you can use the evaluation theorem for section 5.3. But if I give you a problem from section 5.2, where you know they're talking about delta x and Riemann sums, then you have to use the Riemann sum. And you know probably you're going to get one or two where you have to find the limit of a Riemann sum and work it out, because that was something that was important too. But certainly this is very forward-looking, the evaluation theorem. The Riemann sum was used in section 5.2 to get you comfortable with what a definite integral is. But now that you know that, we can use the evaluation theorem. And so look, you get negative 6.75. How many think that's absolutely cool? Yeah, Rodrigo likes it. Ian, Joe, Chaco, John. Absolutely, absolutely. All right, well, way easier, yes. I agree, Zoe. All right. Well, now let me think for just a moment here. Let me bring up something real quick here. I mean, it's clear that antiderivatives are going to be very, very important. Okay, and so that being said, let me go to the book here, back to the book real quick. In section 5.3, they have a table of indefinite integrals. Okay, they have a table of indefinite integrals that you can refer to. Okay, you can refer to this table to help you apply the evaluation theorem. Okay. So let's go ahead and do it. You might want to, this table is in, of course, section 5.3. It comes right before example 3. So let's go ahead and look at another example here. Okay, let's work through this example. Okay, and I think, let me just ask, Betsua, can you hear me okay, Betsua? Maybe just give it thumbs up, or, because I know you were good. Betsua, just please check an email from me. Please check an email from me. Very important that you check this email, okay? So, okay, great, great. And then after class, you can get back to me if you have a few moments, okay? All right, very good, very good. All right, great, great. Thank you, thank you. Okay, so now in the previous example, I computed the antiderivative of x cubed minus 6x all at once. Okay, but sometimes it's helpful, like here I have the definite integral where I have, I have three functions involved. And sometimes it's helpful to use the properties of integrals, which would apply to the definite integrals, because a definite integral is an integral. It's helpful to apply the properties to make life a little easier. Okay, so let's go ahead to the solution here for this. What I do is I write this definite integral in terms of three definite integrals by using the properties of integrals. So like one property is, that the integral of f plus g is equal to the integral of f plus the integral of g. Okay, so the integral of a sum is the sum of the integrals. Well, and the integral of f minus g would be the difference of the integrals. So I think it's clear I can write my original definite integral as what I have here. Are there any questions on that? Okay. And then I notice, well, I have constants here. I have some constants. I have a 2, I have a 6, I have a 3. Let me bring those constants out in front of the integrals. That's another property of integrals, right? If you have the integral of a constant times a function, the constants can be brought in front of the integral. Okay, that's another property. How many remember that property? Okay, very good, Sebastian. Very good, Nicholas. Okay. So now it's time to get the antiderivatives. So the antiderivative of x cubed is x to the 4th over 4. The antiderivative of x is x squared over 2. And the antiderivative of 1 over 1 plus, the antiderivative of 1 over x squared plus 1 is the arctangent of x. And again, you can refer to the table in section 5.3, table 1 of indefinite table of indefinite integrals, and there they are. But you probably, how many remembered that the antiderivative of 1 over x squared plus 1 is the arctangent? How many of you remembered that? Did any of you remember that? Or the arc. John remembered it, okay. Well, and now I'm going to use the evaluation theorem on each of these expressions here. And that's what I've done here. So this is the kind of work I would want to see on the final exam. Okay, and I have to, I guess, I want to stress this. It's important to show work. A few of you on exam 4 lost some points because like for those functions, for those earlier problems where you had to find derivatives of quotients and things and functions like that, some students, not many, but a few just gave me the answer. The derivative is this, the derivative is that. You can't get derivatives unless you work out the rules. So when you compute derivatives, even in you have to show me the rule you're using and actually compute the derivative and work it out. Because this is part of testing. I'm testing your understanding. I know a computer can give you a derivative. Okay, I know that, but I need to see that you can compute a derivative, you know, and using the rules. And it's the same thing for integrals. For a definite integral, using the integral rules, I want to see these steps. Okay, I need to see the steps to make sure that you're understanding the concepts. No shortcuts, please. No shortcuts. All right, so we work everything out. And you know, you're going to get -4 plus 3 times the arctangent of 2. And we can approximate that with a decimal, but you know web assigns are very likely going to want the exact answer. And I have a little picture here that just shows this function, the function being 2x cubed minus 6x plus 3 over x squared plus 1. It shows the function, and it shows, you know, the positive area here, and you have negative area here, and positive area there. And it's clear that the negative area, well, it's pretty close, but the negative area is a little more than the sum of the positive areas, and that's why you get a negative answer for your definite integral, because the definite integral is the net value of all the areas. The book does this example too. The book does this example, but when in example 5, but when they do it, they get, like, for the function here, for your integrand function here, they just get one big antiderivative, and that's okay, but, you know, why not use your integral properties to help you? All right, are there any questions so far? I want to make sure I'm pacing myself right so that, you know, before we go to the next example. We have a few more examples to do. Nicholas is good. All right, thank you, Nicholas. All right, then let's go ahead and we'll move to the next example. All right. Now this one I have a typo class. I have a typo on this. The numerator here, there should be not a 1 here, but a 2. plus, and put a 3 in front of the cosine squared in the numerator. Okay, so we are finding the definite integral from 0 to pi over 4, okay, of, well, the integrand is this part. This is called your integrand. And the integrand is 2 plus 3 times cosine squared of theta divided by cosine squared theta. Okay, so now, this is, if you look in your table of antiderivatives in section 5.3, you're not going to find this antiderivative there. So sometimes what you have to do is you have to rewrite the integrand a little bit in a nicer way so that you can get the antiderivative. It's called simplifying before integrating. Simplifying before integrating. Now let me show you how we would work this. Let me go to the solution here. So what we can do is we recognize that we have a fraction here. 2 plus 3 times cosine squared of theta, all divided by cosine squared theta, right? That's a fraction. All right, and I can break that fraction up into the sum of these two fractions, right? I mean, it's no different than if you had like 1 plus 5 over 8. 1 plus 5 over 8 is the same as 1/8 plus 5/8. Now, what you're always used to doing is having two fractions, like 1/8 plus 5/8, and then adding them together to get, 1 plus 5 over 8 or 6/8. You're used to going in this direction. But hey, we can go in the other direction too. And that's what we did here. I took the fraction with a common denominator of cosine squared theta, well, the denominator cosine squared theta, and I broke it up into two fractions. All right, and then what I'm going to do is, well, of course, the cosine squared theta over cosine squared theta simplifies to 1 over 1, and I'm left with, and now what I have is I have the integral of the sum of 2 over cosine squared theta plus 3, and I can write that as the sum of these integrals. Please let me know if you have any questions. All right, Yaki's good, good. And 2 over cosine squared theta, by the way, is the same as 2 times 1 over cosine squared theta, right? We can write 2 over cosine squared theta as 2 times 1 over cosine squared theta. But from your trig days, what's 1 over the cosine of theta equal to? Secant of theta, that's right. Right, Nicholas, right, Sebastian. And so 1 over cosine squared theta is secant squared theta. And I want to note too, class, in this problem, you notice when I integrate, I'm integrating with respect to theta. So like the previous two problems, I was integrating with respect to x, so I had a dx. But this problem, my independent variable is theta. So I'm integrating with respect to theta, and that's why I have a d theta there. Okay, you have to have it has to match, you know. Okay, well now the antiderivative of 3 is just 3 theta, that's easy. And the 2 in front, the 2 times secant squared theta, I'm going to bring the 2 out in front of the integral. And now what I do is I apply the valuation theorem here. And then the antiderivative of secant squared theta is tangent theta. That's another one of those common antiderivatives. Let me know if you have any questions. All right, may I go to the next page? Are we good up to here? Okay, but Sue is good. All right. Well, the tangent of theta, we need to evaluate it at pi over 4 and 0. And so we do that. The tangent of pi over 4 is square root of 2 over 2. And the tangent of 0 is 0. And so you're going to get your answer. It's really beautiful stuff. It really is. Wait a minute, I have an error. Tangent of pi over 4 is not square root of 2 over 2. The sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2. What's the tangent? What's the tangent of 45 degrees? 1. Good. So let's correct that. Let's correct that. This should be a 1 here. And so you're going to get then, one moment here. One moment, class. This is the example that I kind of rushed it, you know, because I wanted to get it in for you. I wanted to just try to give you a little bit of a variety. Because, you know, this homework assignment is going to be, for 5.3, is going to be due Wednesday. And there are a fair number of problems in it. They don't necessarily take real long time to do, but, you know, I think a variety is good. Okay, 2 plus pi, 2 plus 3 pi over 4. I feel good. And then the tangent of 0 is 0. How many were ready maybe to correct me? Was anybody thinking, Dr. Duty, think you might have an error there? Okay, Zoe was ready. I beat her to it, but she was ready. She was getting ready. All right. Very good. Very good. I see, Zoe. I see. Well, I understand. Yeah, because with the professor, occasionally even professors make an error. But the key is, can you catch it? That's the key. But no, you were right, Zoe. You were right. All right. All right. So now there are. I want to say it's the right way. There's important applications to the evaluation theorem. Okay, important applications, and for that I want to get to another example. So I will get to that example if we're good. Are there any questions? All right, very good, very good. Betsu is good. All right, then let me see here. We need to do a word problem. Oh yes, with velocity. How many remember the particle moving along a line back and forth? How many remember those kind of problems? It's been a little while. But yes, Ian, yep. So let me give you a moment to copy this example down. And what it is, see, there's a nice interpretation of the evaluation theorem. Evaluation theorem really is a statement of net change. And the book gives some examples of applications that right after example 6, there are some applications that talk about how the evaluation theorem can be interpreted as net change. So I'll let you look at that, but this is one of the examples, and I'm going to do this one with you. All right, so let me give you a moment to copy this down. Okay. Okay, so a particle is moving along so that its velocity at time t is equal to t squared minus t minus 6. And what we want to do is we want to find, first of all, the displacement of the particle during the time period. The displacement is the difference between where the particle is at t equals 1 second and t equals 4 seconds. That's the displacement of the particle. And then we want to find the distance traveled during the time period where t goes from 1 to 4 seconds. So let's go ahead and work the problem out. May I go to the solution? Does everybody have this copied okay? Okay, John's good. All right. Well, then let's go ahead and move forward if everybody's good. So first of all, I just want to give give you a intuitive feel for this, how to work this problem. So remember, by the evaluation theorem, if you have an antiderivative of your function, then the derivative of your antiderivative equals the function. And so we can express our function f of x in the evaluation theorem as the derivative of the antiderivative of that function. But by the evaluation theorem then, the definite integral, the integral from a to b, of the derivative of your antiderivative function is just equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. This is known as the net change theorem, and it's just basically recognizing that we can write in the antiderivative, the derivative of our antiderivative for the function, little function f of x. Okay, let me give you a moment to copy that. Okay, so the question is, why, how does this help us? Well, remember that the velocity is the derivative of position. S is position. And so if we were to apply the net change theorem here, how would we apply that? Well, we would recognize that the derivative of position is velocity. I mean, we know that. We know that from what we learned earlier. So that means then that the integral from time t1 to time t2 of the velocity with respect, the integral from t1 to t2 of the velocity with respect to time t is simply the difference of the position of the particle at time t2 minus the position of the particle at time t1. This net change of position or displacement, that's called the net change of position or displacement. So, you know, in the problem here, they say find the displacement of the particle during the time period. Well, we can use the net change theorem to find the displacement of the particle. Instead of, and of course, instead of the derivative of capital F, we have the derivative of S of t, but that's just equal to V of t, you see? And so let me know if you have any questions before we move on. All right, let me know when I can go to the next page. Well, actually, I'm not ready to go to the next page, right? There's a little more down here. So this means then that the displacement of the particle between times of 4 seconds to 1 second would just be the definite integral from 1 to 4 of Vt dt. Okay. And now it's just a matter of computing the antiderivative of t squared minus t minus 6. All right. So let's then continue the problem. All right. So the displacement, S4 minus S1, then, the antiderivative of the velocity would be then t cubed over 3 minus t squared over 2 minus 6t. So I just did the and we're evaluating it at 4 and 1. And I didn't really, there were no integral properties to use. So, And that's just a matter of computation. It's just a matter of computation. And, you know, I substitute 4 into, you know, this is S sub 4 here. And this is S sub 1. Okay, and I mean, if you get, you know, when you get down to this step here, I mean, what I did was I worked it out, getting common fractions and then computing it. But I think probably some of you, if you got to this step, would probably then just use the mathfrak feature on your calculator to compute it all. And you will get negative 27/6, or which is negative 9/2. And it turns out that after 1 second, the particle's position is negative 37/6, which means it's 37/6 units to the left of the origin. And after 4 seconds, the particle is negative 64/6. So it moves further to the left of the origin, you know, during the time period, the net result. Okay, so, and I'm going to give you, of course, a chance to copy and everything, but I'm just trying to. This means the particle's position at time t equals 4 seconds is 4.5 meters. 4.5 meters because the difference between S4, S of 4, and S sub 1 is negative 9/2. That equals negative 4.5. I'm going to turn my, I don't want, hold on here, one moment, class. That'll be negative 4.5. One moment. Okay, and so this means that the particle's position at time t equals 4 seconds is 4.5 meters to the left of the particle's position at the start of the time period. And the start of the time period would be when t was equal to 1 second. Okay. So all you're doing is finding, you know, from where the particle started, the position this particle started, to where the particle is now at the end of the time period. That's your displacement. We're not now analyzing what how the particle moved. I want to be careful. I think we're just saying, hey, during this, after this 3 second time period, between 1 and 4 seconds, the particle has moved 4.5 meters to the left from when it started. Okay, are there any questions on that before we move on? All right, may I move on? Are we good? All right, very good, very good. Now part B says, find the distance traveled during the time period. So for distance, we have to account that we have to study how the particle acts, you know, to find the distance. So what we have to do is we have to, well, to help you understand how we're going to get this, I said, well, let's analyze the velocity. The velocity function is t squared minus t minus 6. That factors as t minus 3 times t plus 2, right? That factors into that. And I make a little chart. Okay, I write down the t minus 3 factor. Okay, that equals 0 at t equals 3, but is negative when t is less than 3 and greater when t is positive when t is greater than 3. The second factor, t plus 2, that's a plus, right? T plus 2, that factor will equal 0 when t is negative 2. Okay. And it'll be, that factor will be negative when t is less than negative 2, and positive when t is greater than negative 2. Now, for our purposes, we're really, time is, can you have negative time? Well, I won't go into that, but what we care about here, but let's just focus on the problem at hand, and let me, hold on here, let me just, one moment here. So then the velocity, I know where the velocity is positive and where the velocity is negative based on the chart, because you just take the product of your factors, okay, and study the results. So like for instance, when t is greater than 3 for this part, both factors are positive there, and a positive times a positive is a positive. If t is between negative 2 and negative 3, and if t is between negative 2 and 3, one factor is negative, the other factor is positive, the product is negative. Okay, and so our velocity, but what we care about is the interval from 1 to 4. So I'm really only going to use a portion of this chart, the portion from 1 to 4. And the velocity is negative from 1 to 3, because when t is between negative 2 and negative 3, or when t is between negative 2 and positive 3, the velocity is negative. When t, though, is greater than 3, the velocity is positive. So the velocity would be positive over the interval from 3 to 4. So this means the particle has to move to the left when, over the time period from 1 second to 3 seconds, particle has to move to the left because the velocity is negative. It's going to stop then at time t equals 3 seconds, because at time t equals 3, the velocity is 0. And then the particle is going to move to the right after that, because the velocity is positive when t is greater than 3 seconds. Okay, and so this is a picture. I have a picture here of how the particle travels along that line. Let me give you a moment to catch up here, okay? We'll talk about the picture. Okay, so what I did was that you've seen similar graphs in earlier on this, but the axis is position, and when t equals 1, the position of the function is going to be negative 37 over 6. That just comes, hold on here, one moment. One moment. Let me see here, one moment, class. Let's see here. That comes from the previous page. That comes from the previous page. Here's position of the particle at 1 second. That's negative 37.6. And then here's the position of the particle after 4 seconds, negative 64.6. So that's how I get these, that's how I get this information here. Okay. Now, the distance traveled, so the particle moves to the left, starting at t equals 1, right there. What happens after 1 second? The particle moves to the left until it reaches, for 2 seconds. And then when at time equals 3 seconds, the particle stops, and then it's going to reverse course and move to the right. That's verified by the velocity function that we looked at above. So the displacement, the distance traveled, would be the absolute value of S3 minus S1, okay, plus the absolute value of the position S4 minus S3. Okay, so that would be your it's like taking this distance here, okay, that's S3, S of 3 minus S of 1, but absolute value of it, and then adding this distance here, which would be S of 4 minus S of 3, the absolute value. Okay, now you'll notice that the difference in position, S of 3 minus S of 1, is negative. But we take the absolute value to make that difference positive. And then the difference between S of 4 and S of 3 is already a positive distance because the particle's moving to the right from time equals 3 to time equals 4 seconds. Are there any questions on the little picture here? It's going to be helpful for what's coming up. Okay, so how can we find the displacement? Well, here's how we do it. I'm sorry, how do we find the distance traveled? Here's how we do it. The distance traveled from time equals 1 to 4 seconds is going to be the absolute value. It's going to be the definite integral from 1 to 4 seconds of the absolute value of the velocity. Okay, because we have to take the absolute value of the velocity because the evaluation theorem, or which is now the net change theorem, the net change theorem gives you the difference of the positions of the particles. Sorry, the net change theorem says that the integral of the velocity is the difference of the two positions of the particle, starting from your beginning time and end time. But when we're talking about from 1 to 3 seconds, the velocity was negative. And so you have to take the negative of the velocity. Okay. The velocity was positive, though, from t equals 3 to 4 seconds. And so for that part, you don't have to take the negative of the velocity from 3 to 4 seconds. Again, it goes back to the picture. If he goes back to the picture, this difference here is a negative difference because s sub 3 minus s sub 1 is negative. So we take the absolute value of that, which is why then we have to take the negative of the velocity. On the other hand, s sub 4 minus s sub 3, which is this part here, that's a positive distance. And so we don't need to take the absolute value of the velocity. And that's why we get this. And this is going to take a little time to get comfortable with. But you're going to have the recording and you have the picture. So now it's just a computational problem. Okay, just a computational problem. And I'm working out all the steps. And I'll let you copy this down because I want to try. I think I want to give you some time to work in class on your new assignment. So let me give you a moment to copy that down. This is all just computation here, but let me know if you have any questions. Okay, may I move to the next page? Are there any, to the final page, are there any questions on what you see here? All right, well, the final page, basically then, it's just finishing out the the work. And the distance traveled, it turns out, is going to be approximately 10.17 meters. And what I've done here is I've drawn a picture of, the velocity function was t squared minus t minus 6. And I've drawn that velocity function here for you. I've drawn it. And I'm giving you a pictorial representation of what the displacement is. So on the graph, I've drawn an area A1, which is in an area A2, right? And so the displacement is just going to be negative A1 plus A2, because the A1, well, that area is negative area. So we have negative A1 plus A2. That was just when we computed the definite integral using the evaluation theorem. The distance, on the other hand, is going to be the integral from 1 to 4 of the absolute value of the velocity. And that's just going to be the sum of both areas. That's geometrically what we've done. All right, so let me give you a moment to copy that down and see if you have any questions. There are a lot of examples in the book where they talk about applications. We did a velocity application here, but we can interpret the net value theorem or the evaluation theorem in terms of many applications. Chemistry, cost, the rate of growth of a population. I mean, there's a lot of well, you look at the applications, you look at the different examples in the book, okay, and they're there for you, and they'll be helpful for even maybe a few homework problems, maybe like multiple choice. You might see a few where they could be helpful. You got to do a little reading, right? Okay, so let me know if you have any questions here. This is really a step into a bigger world for you all. Look at what you can do now using calculus. Look at the kind of problems you can do. It really opens up a bigger world. The world wouldn't be what it is today without calculus, right? We wouldn't have the engineering we have and the science we have. It is cool, Yaki. I agree. I agree. Okay, so let me know when you're done copying, and I assume there, if you have any questions, but I want to move forward, let you work on classwork a little bit, but I don't want to. Well, I think There probably, are there any questions? I won't click it off here, but are there any questions? If not, I'll stop the recording. Okay.